माहित नाही. कशी आहे की तू खरंच मला त्यांना त्रास होतो बरं का.
Recording stopped.
Am I audible?
Yes, sir, you are audible, sir.
Okay, thanks.
Recording in progress.
Okay, so we are already 210. So I think it's high time that we start. Okay, so we started to talk about graphs and trees. Okay, last time. So what we did is that we introduced notion of graphs and okay, this is too much. No. Okay. Okay. And then we introduced the notion of graphs. And then we talked about different kinds of graphs. And the first graph that we considered was this residence-doctor graph. And that helped us introduce the notion of bipartite graphs. Okay. And then from there, we got into the notion of paths and cycles. And then we heard the notion of walks and paths. And then we saw the notion of closed walk, cycles. Okay. And then we had a following statement: if a graph G has an odd cycle, then it is not bipartite. But it was not clear to us what is the meaning of graph G has an odd cycle. And then we introduced the notion of subgraphs. Okay. And then we introduced the notion of edge deletion and vertex deletion. And then we showed that if G is bipartite, then any subgraph of G prime is also bipartite. Okay. So the first exercise which I gave you is that if a graph G has an odd cycle, then it is not bipartite. And then that's the first statement we'll start with today. And then we introduce this notion of degree of a vertex. And then we introduce this notion of handshaking lemma. So let's start from the handshaking lemma, and then we'll prove the bipartite statement, and then build from there. Okay. So would anybody like to tell me why this handshaking lemma proof, like why this statement is true? What do you think can be an intuitive proof? Anybody? Just unmute yourself and ask. It's just a normal class. Okay. So if someone knows or has an intuitive idea of the proof, can you put +1? That in any graph, summation of degree of V is equal to 2 times the number of edges. Okay, nobody is putting one. Okay, so suppose I have an edge. Okay, 2 vertices make an edge. Yes, Sanjeev. Then Sanjeev, you can just unmute yourself and speak. It's perfectly fine. I mean, we all make mistakes, so don't worry about making mistakes. Okay, so 2 vertices make an edge. So now tell me yourself, what is a degree? Degree of a vertex is basically number of edges incident to a vertex. Okay, now an edge can contribute degree of how many vertices? 2. Okay. Is this clear to everybody that an edge can contribute degree of 2 vertices? Is this clear to, if it is clear to you, put +1. If it is not, put -1. Okay. Okay. Okay, fine. Then is this proof clear now to everybody? Okay. Then what is the left-hand side counting? So left-hand side is counting. Let's compute. What? If someone was saying something, please tell me. Okay. So what is the left-hand side counting? It is counting the degree of every vertices. What is right-hand side counting? Okay, look, whenever I count a degree, I count number of times and edge is incident on a vertex. But now notice how many times the same edge is counted in the left-hand side? Twice, right? If the edge is incident to U and V, it counts once for U, it counts once for V. And this is why this is 2 times E. Okay, that's it. So there is no more. Okay. Now let me ask yourself a question. How many odd degree vertices a graph can have? Okay, so suppose, can it be 3, 5, 10? Which of them is possible? Like, how many odd degree vertices a graph can? A vertex is said to have an odd degree if the number of edges incident to this is odd number. Okay, and now I'm asking, can a graph have 3 odd degree vertices? Can a graph have 5 odd degree vertices? Can a graph have 10 odd degree vertices? Which of these statements do you think is true? Okay, Praveen. So you say that there can be a graph with 3 odd degree vertices. Okay, can you construct such a graph? No. Why? Yeah, none. Someone told me none. So there is a reason for it. Let's see. So we just now saw, see how you can assert something from somewhere. What did you say? Summation of degree V is 2 times M. Say M is number of edge. So what is this number? Can someone tell me? Is this even or odd? What is this number? Is this even or an odd number? What is this? Even, right? Because 2 times any number is only going to be even. Perfect. Very good. Okay. Okay. Now, suppose you had odd number of, look at the left-hand side. Suppose I had odd number of odd degree vertices. So suppose I have, say, some odd number, say 2k plus 1 vertices of odd degree. Okay. And the remaining is number of vertices of even degree. So look at this. So I can write down this sum as equal to summation V in V, degree of V odd. Degree of V, summation V in V, degree of V is even. Okay. Now tell me what this sum will be. Is this even or odd? What is this sum? So you are summing some even number, like you are summing some number of vertices which has even degree. Is this even or odd? Okay. Degree of V is even. Right. So 2 plus 4 plus 6 is even, right? Whatever it is, like how many even numbers you add, you're always going to get an even number. Okay. So suppose this is a number X. So now let's try to understand. Summation of degree V, V in V, degree of V is odd. Now this is 2 times M minus some X. This is even, this is even. So what is this number? Is this even minus even is what? Odd or even? Even. Okay, great. Okay, so now what are we saying? Look at the summation of degree V, V in V, degree of V is odd. This is equal to even number. Now you tell me 3 plus 5 plus 7. Is this even number or odd number? Odd. Exactly. So imagine yourself that you can always pair 2 odd numbers and they will give you even number, right? Because what is odd number? Odd numbers are of the form, say, 2k plus 1, 2l plus 1, right? So if you add 2 odd number, you are going to get what? You see, 2 into k plus l plus 2. So this is an even number. So if you have odd number of odd numbers, this is always going to be odd, right? So what does this statement imply? That this left-hand side, where we are going to sum up odd numbers and they are going to be equal to even number, then this can't be odd. So what does it implies to us? That in any graph, number of odd degree vertices are even. Okay, is this fine? Is this fine to everybody? Is this proof fine to everybody? If it is fine to you, please +1. So you see, starting from some basic simple fact, we were able to derive some other simple fact. Okay, just 1 second. Okay, good. Okay, so moving on. Okay, so we saw, and another thing now I would like to, okay, what was the first statement we would like to prove? So we wanted to prove the following statement. Copy. Okay. So last time we saw the following statement. Okay. I would say proof attempt. I will not even say proof. Okay. If a graph G has an odd cycle, then it is not bipartite. But what did we saw last time? We proved if a graph G is bipartite, then it implies every subgraph of G is bipartite. Right? Do you remember we proved this? Is that fine? Yes. Okay. So what is the contrapositive of this? What is a contrapositive statement of this? You have learned some logic or something in the first unit. What will be a contrapositive of this line? Can anybody say to me? What is a contrapositive? A implies B. What is a contrapositive? So contrapositive is, let G be a graph. Okay. If there exists a subgraph, of G that is not bipartite, implies G is not bipartite. Is that fine? Look, what is it? If a graph G is bipartite, then every subgraph of G is bipartite, right? But what's the contra? If I can find even one subgraph of G that is not bipartite, implies G is not bipartite. Is that fine? Is statement fine to?
Yes.
Okay, tell me your voice is not audible properly. Okay, fine. Okay, so what does this imply? If a graph G has an odd cycle, okay, then it is not bipartite. This is obvious now. Why? Because if a graph G has an odd cycle, then it implies that it has an odd cycle as a subgraph. How? You just keep the edges on this cycle, delete every other edge, delete every other vertex that do not participate on this cycle, then what you are left with? You are left with a subgraph of my graph, which is an odd cycle and which we have already seen is not bipartite. Okay? And then you are done. Right? So this is how we can prove lots of interesting statements starting from some of the things that we see or that we prove. Okay? Okay. Okay. So moving on. Okay. Moving on, given that I have a certain amount of time. Okay. Okay. So let me introduce some other families of graphs. Suppose you are 5 best friends. And I want to make a friendship graph for 5 best friends. How will it look like? Say, sorry, 6 friends, 6 best friends. How will this graph look like? If I try to draw a friendship graph of 6 best friends. Okay. So how did we draw a friendship graph? We draw a friendship graph. If 2 people were friends, we draw an edge. And these are 6 best friends. So will it be a star? Can there be? So what is the meaning of this? What is the meaning of best friends? Okay. He knows him. Everybody knows everybody else. It's not a pentagon. This is called complete graph. Okay. Because between every pair of vertex, there is an edge. Okay. So what is the property of this? Between every pair of vertices, we have an edge. Right? Is that fine? Right?
Yes, sir. Yes.
Okay. So if number of vertices, okay, if the number of vertices in this graph is n, you denote it by kn, and you also call it complete graph. What do you call it? Complete graph. Okay. There is another term in graph theory which is useful for this. It is called clique. Okay. Okay. So basically think of what is clique. So I have a 6 best friends. It means for every pair of friends, they know each other, right? So between any pair, there is an edge. Okay. So a closely associated, okay, a closely associated graph is the following. Okay. What is a closely associated graph? Okay. Is that you look at a bipartite graph, okay, and imagine that in a bipartite graph, every vertex in the A side is neighbor to everybody else. Okay. Like for any U in A and V in B, we have an edge U comma V. Okay. Then these are called complete bipartite graph. And we will need this graph when we will learn one other class of graph. That is why I'm introducing it. Complete bipartite graph. And it is denoted by KMN if the side of A is M, side of B is N. Right? So for example, what will be K33? Okay. And there are some special graph classes. Okay. So tell me, what is K15? How will K15 look like? Anybody? How will K15 will look like? Yes, Wagmere, would you like to try?
Sir, every element is connected to other 5 element.
Okay, so in the left
That-
side, how many vertex will I have?
1,
One, very good. And the right side, how many vertex do we have?
5.
Okay, so let's draw them 5, right? 1, 2, 3, 4, 5. And now it's complete. So this vertex is attached to everybody else in the right side.
Yes, sir.
So let's draw them. Very good. Right? Yes. So Winston, you're
Yes,
right.
sir.
This is basically what is called star graphs. So what are the star graphs? It's a complete bipartite graph where one side has how many vertex? One vertex. Okay. So star graphs are a special case of complete bipartite graph. Okay. With one side has exactly one vertex. Okay, is that fine? Okay, so let me go back to my bipartite graph. I really like that graph. Okay, that hospital residence graph. Do you remember? Okay, we have not talked about them very nicely. Okay, so do you remember this hospital doctor graph that we made? Okay, so here it is. So what was it? We have a residence doctor, okay? So D1 to DN, and we have hospitals H1 to HM, and every doctor has choice. I would like to go hospital HJHI. So there are no edges in the doctor side. There are no edges in the hospital side, but there are edges going from doctors to hospital side, where doctors tells me that what is my preference or which hospital I would love to go for my residence. Okay. Let's see. Okay, let me copy. Okay, so let me see. Okay, so what are these doctors looking for? Right, doctor, you'd like to have a match to other, right? Do you get my point? Okay, imagine that one doctor can go to how many hospitals for internship or residence, whatever you want to call it. Can a doctor be part of 2 hospitals at the same time as a resident? I mean, theoretically, yes, but practically, no, right? So if every doctor would like a hospital, okay?
कुछ नहीं करती पता फिर भी इसको टाइम लगता
All of you are recorded. Okay, so every doctor would like a hospital, and imagine that every hospital has only one post left. Every hospital can only take one doctor. So we are in this situation. Every doctor would like a hospital, and every hospital can only take one doctor. And suppose you are an agency and you provide this. You are an agency, okay, and your central agency, and you like to match doctor to the hospital, right? That's your job. Okay, so what is the doctor hospital pair will refer to in this graph? Is it an edge? It is a vertex? What it is? So how will you match? You say, look, Dr. 1 goes to some hospital A, Dr. 2 goes to hospital B, right? So on and so forth, right? Now, what is this? These are basically your edges in your graph. Now, you tell me, is it possible that same hospital can be here as well as here? Like, say, SRM hospital, right? Is it possible that you can assign 2 doctors to the same hospital? No, because then it will violate the fact that every hospital has only one post left. Okay. Similarly, same doctors, say Mohan, can he be assigned to 2 different hospitals?
No.
Exactly. So what are this property of this set of edges? This set of edges has a property that, say, E1, E2, EL. What is the property of this set of edges? That pairwise, they are vertex disjoint. Meaning, if you look at any 2 edges, okay, they do not have any vertex in common. Okay. So these objects are called matching. What are these called? Matchings. Okay. So let's take an example. Can someone tell me a matching here? Anybody? In this particular graph, can you tell me a matching? Can you match 1 to anybody, 2 to someone? Okay. Someone told me 3C. Okay, 1 matching. And then matching is set of, can I match 1 to anybody? Okay. He's saying match. Okay. And what else? Where can I match 1 to? I can match 1 to B. Notice 1V, 2A, 3C, correct. Why 1A, 1B, 2A, 2B, 3C is matching? 1 appears in 2 of the edges. Why that is a matching? You tell me. What did I tell you? What is the property of matching? You look at any 2 edges, they do not have any vertex in common. So look at 1B and 2A. Do they have any vertex in common? No. Look at 1A and 3C. Do they have any vertex in common? No. Look at 2A and 3C. Do they have anything in common? No. So this is called a matching. Okay. Is that fine to everybody? That one, do you understand the concept of matching? Okay. And this example? If yes, put +1. If not, ask question. Okay. Okay, let me see. Okay, in this graph, can you find a matching? Can you find a matching in this particular graph? Okay. Yeah, but like, I never say that matching needs to pick up every vertex from both sides. Matching just means it's a set of edges which does not have pairwise disjoint intersection. So for example, here I can find a matching 1A, 2B. That's it. Okay, this is a matching. But what is the property of this? Okay, there is no matching that saturates every vertex in A side. Can you prove this? There cannot be any matching that saturates every vertex in A side. Can you prove this? Anybody? Look, left-hand side has strictly more vertices than the right-hand side. And we are trying to find a set of edges so that they are pairwise disjoint. Then how can I have, like even if I saturate everybody in B, there is still one vertex left in the A side. Okay, so there cannot be any matching that saturates every vertex in the A side. Prasad, could you mute yourself? Unless you want to say something. Okay, I muted you. Okay, fine. Okay, so is this idea clear to you that in this particular graph, I cannot have a matching that saturates every vertex in A side?
Yes, sir.
Okay. Okay, so let's apply our brain further. Suppose I have a graph A and a graph B. Okay. And I want to say to you, what conditions can be put on A so that there exists a matching, that saturates every vertex in A side. Right? So what small condition can you think of? If I want to find a matching such that every vertex A participates in that matching, so what should you say then? Can you at least tell me one condition that you think it must satisfy, otherwise there's absolutely no hope?
Sir, number of vertices on A side equals to number of vertices on B side.
I don't care about B side. I'm not trying to match every vertex in the B side. All I care about is that I want to match every vertex in the A side. Then it should be equal or at least
Greater than.
So all I care about that the cardinality of B should be greater than or equal to cardinality of A. Am I right? Is this fine?
Yes, sir.
Okay. Imagine yourself that I have a subset here, say called X. Okay. Okay. And look at the vertices which he sees here. Right? Let's call this Y. Right? So what is the property of this? This vertex do not have a neighbor outside this set Y. So this is what is called. So what is Y of Y? Is the neighborhood of X. All the vertices which X is adjacent to are contained inside Y. Suppose, what do you think? If the cardinality of X is strictly larger than cardinality of Y, do you think there can be a matching? Because if there is just a matching that saturates every vertex in A, that also be saturating X, no? Is this idea clear to you? Look, if I have a matching, suppose if I have a matching that saturates every vertex in A, right? Every vertex in A participates. So every vertex in A participates. Now you pick up a vertex in X. So suppose these are my X vertices, right? They are also matched by edge to some vertices, right? Right. Now, if the total number of vertices they could see which is neighborhood of X, is strictly less than X, can we have a matching saturating A? Do you understand what I'm asking? You said that the cardinality of B should be greater than or equal to A. I'm telling you that, look, that is not enough. I can also say that look at any set X in A and look at the vertices which he is adjacent to. Look, X can be only matched to the vertices which he is adjacent to, right? If the number of vertex he is adjacent to, right? So imagine yourself, okay? We are in a marriage market, okay? Okay, although I'll show you. Okay, and suppose this is 6 guy. And suppose okay. Now, okay, can you have a matching here? Sorry, what I'm drawing. Okay, yeah, let's see. Okay, how many vertex do we have in the left-hand side? How many vertex do we have in the left-hand side? 6. How many vertex do we have in the right-hand side?
7.
7. Okay, so our B is definitely larger than A. That condition holds. But now look at these 3 people. Okay, A, B, C, E, and say little alpha and beta. Okay. Now ABC only sees alpha and beta. Am I right? Right. So if we can match A to alpha, B to beta, can C be ever matched to anybody else? Imagine the 3 people who only are interested in 2 women. Okay. Then we can only match 2 pairs of such men and women. Is that clear to all of you?
Yes, sir.
Yes or no? Right? So what does it imply? Is that, look, not only cardinality of B should be greater than or equal to A, but one condition is that for every X subset of A, neighborhood of X should be greater than or equal to cardinality of X. Right? So the number of people, number of vertices X could match to should be larger than its size. Otherwise, there cannot be a matching. Okay. And this is what is called as Hall's condition. Okay. And this is what is called necessary condition. Okay. I'm not going to give you a proof. Okay. But greatly, this is also sufficient. What is the meaning of that? Let me at least write it down. Okay. So what is the theorem known? Okay. You should check it out. It's called Hall's theorem. Okay. What it says, let G, A, B, E be a bipartite graph. Then there exists a matching saturating A if and only if for all X subset of X, N of X is greater than or equal to cardinality. So what does it tell us? Look, if there exists a matching, then this condition is anyway satisfied. But in fact, if this condition is satisfied, we can always find a matching that will saturate every vertex in A. So this is what is called classically Hall's theorem. Okay. This is a concept of matching. This is a concept of Hall's theorem. Okay. Unfortunately, proving this will require me one whole lecture. So I will avoid it. So, but I just wanted to tell you that, like, when you try to think something in graph theory, think about what condition could be come up with that this thing statement or something could be true. And many times what happens in graph theory that those conditions are also sufficient. Okay. Okay. So, okay. So having dealt with all this, let me introduce a couple of more. I still have some 7-8 minutes. So let me. Okay. So what I have not taught you up until now is sorry. Okay. Okay. So let me introduce, okay, notion of another kind of object. Path and cycle. Okay. So what is a Hamiltonian path and cycle? Okay. Do you remember what path was? Path was V1, V2, some VL, such that no vertex is repeated. Vi plus 1 is an edge. Okay. And okay, that's it. Okay. So now, if every vertex in my graph, in graph, participates in P, then P is called Hamiltonian path. Okay. And now, if V1 equal to VL and every vertex participates, then it is called Hamiltonian cycle. Hamiltonian cycle. Okay. Let's see if you can. Does this Hamiltonian, does this graph have a Hamiltonian path? Anybody? So what is a path? Hamiltonian path? A path that consists of every vertex. Can anybody tell me an Hamiltonian path here?
Yes.
Okay, which one? Tell me. How will we go? Tell me. Show me a path in this graph. One, 6. How will I go from 1 to 6? There is no edge between 1 and 6. So okay, 1 to 2, 2 to 3, 3 to 4. Oh, sorry, like my bad. Let's call it. Okay, otherwise it becomes 6, 7. Okay, you're right, but what you did is correct. 4 to 5, 5 to 6, 6 to 7. 100%. So this is a path, no vertex is repeated, and every vertex participates into this, and hence this is a Hamiltonian path. But does it have a Hamiltonian cycle? Does it have a Hamiltonian cycle? No. Why? Okay. So there is some, can you tell me one simple line why it does not have a Hamiltonian cycle? I will be very happy if you can tell me one word. Why do you think it does not have a Hamiltonian cycle? Of course, you can see there is no Hamiltonian cycle, but why? Exactly. It has a pendant vertex. But what is a Hamiltonian cycle? It's a cycle, right? Now, it means in just this graph, every vertex participates into 2 edge, right? So every vertex has degree 2. But in this graph, 1 and 7 has degree 1. So there cannot be a cycle containing every vertex and has this property. Okay. So that is a notion of, what is that called? Hamiltonian cycles. There is also a notion which let's introduce today. Okay, so this is about traversing the path. Okay, what about traversing the edges? Okay, these are called Eulerian cycle or circuit. Okay, so basically what happens is that, like, it's basically now you write down E1, E2, E3, dot, 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 some, right? Okay, so like it's a path of edges. Okay, so we will next time what we will try to do on next Tuesday, we'll start from notion of Eulerian cycle. Okay, and then move to trees, directed graphs. Okay, and on next Friday we will talk about 3 algorithms. Okay, so that will be our plan. Okay, and the next Friday we will talk about BFS, DFS, and minimum spanning tree algorithms. Okay, so next class we will spend first what Eulerian circuits are, some necessary condition to have an Eulerian circuits or cycle, introduce a couple of definitions with respect to directed graph, spend the rest of the time talking about trees, why they are important, why they are interesting. And finally, in our last lecture, which is given to me, I will tell you something about how to traverse these kind of, like, what the algorithms, right? So when we try to talk about algorithms, we will have to first think about, up until now, I have never told you how graphs are represented on computer, right? On computer, you cannot draw or write like this. Computer cannot understand this form of writing, right? If you write a computer program, how can you represent a graph? How can you give as an input a graph to the computer program, right? So that is called representation of graph. So that is, we will talk about either in the next lecture or in the last lecture when we will talk about algorithms. Okay, so that's all that I want to tell you today. Okay, what I will do, I will pass on my lecture notes. Either I will put it in the folder itself on my drive, as well as my videos. You can have access to all that. Okay, is that fine? So I'm done for the day.
Yeah.
Please
Thank
let
you,
me know
sir.
if you have any questions.
Sorry, sir. Thank you, sir. So I just want to make some announcement
Please go
for
ahead.
the students. Yeah. So students, for your second IE, whatever the portion we have covered from the third unit, okay, that would be there, student. Okay, and for A and B division diploma students, I'm sending one link for the Google Classroom. So please join that link, A and B division diploma student. Okay, so I hope everyone is clear with the portion that you will have for your second IE. That is the portion today, up to today, whatever the portion we have covered from, sir has covered from the third unit, that would be there, sir. That would be there for your open book test. Okay, I hope everyone is clear with this. Thank you, sir. Thank you.
Okay. So can I end the lecture now, Harsha?
Yes.